All right, so hello everyone. So this will be the second half of the first workshop where we begin to talk a little bit about doing some of these calculations in MATLAB and working within the system. So once you've opened up MATLAB, you're typically going to add a new script, and then that'll pull up this editor window right here, which you can begin to write code in. So you also have this command window, which you can just write stuff in, or typically you'll just write, help, so you might say help if statement or something, and then it's going to go in and it'll tell you about, about the statements, right? So I use that for a lot, and then I use this workspace a lot. So as it's calculating things, you can see what they are. So let's start. So typically I like to start with like a clear all, which clears all the variables, and close all, which will close all the figure windows. And then if you do two little, and you can even, some people will do like kind of a title across the top, so this is our electrochemistry calculations. And so you see some people will have fun with this and do some bunch of stuff, but I'm kind of simple, so I usually just do a couple and then you can see what it is. So we have our electrochemistry calculations, and then if you do two, it's going to do in a space, it'll do a section. So this might be cell voltage, right? And so, for example, maybe we'll do like H2O, and we'll do it for when it's liquid. And what we'll say is, first we set up it's a vector, right? So that's why you do these kind of square brackets, 286, 0.07. And so that makes it kind of a row vector, and then the semicolon will make it so it does not show up when you run the code. So if I don't have a semicolon, you'll see any calculation that I do, it'll output it on the screen. So if I want to suppress it, then I can run the code, and then it won't output it. Then usually I'll make a comment about what it is. So this is the enthalpy and entropy at STP of H2O in the liquid phase. I usually like to say like in kilojoules per mole and kilojoules per mole per Kelvin. And maybe some people like to see in mole Kelvin. Right, and then so we could and then you can copy these lines. So just Control C, Control copy. Right, and this may be in the gas phase. Right, and so we have gas phase. And then we're going to have negative 242, 188. Right, and then go to the end here. So what we'll have to do next is maybe let's say we wanted to add these two vectors and just have one vector for waters, or one, and make it a matrix. So we could say H2O is equal to H2O, that's a liquid, in the first row, and go to the second row and do H2O, that's a gas. So that'll put the two vectors together in one matrix. So when we run it now, what you'll see is we'll have this H2O matrix, and it'll have the two together here. All right, and then we'll also need H2, which will be equal to 0.131. And this is copy and paste this. So both of these will be in the gas phase. Pasted out in the wrong line, huh? So Control X, Control Paste. And just copy paste this whole thing. One line lower, and we'll have O2. Right, and so this is 0.205. So this is enthalpy and entropy and entropy of oxygen. Right? Okay, so we need to calculate the change in Gibbs free energy. So we might also need the temperature, which we'll put in here. It's like room temperature. So temperature in Kelvin. And then we're going to write that well, we have to decide if it's going to be liquid or gas, right? So we'll say if T is greater than 298, so, or sorry, 373. So if it's greater than 100 degrees Celsius, where water boils, then we'll just assume that water's, so this isn't strictly true that, water can exist at gas phase at lower temperatures. But we'll just use this as kind of our first assumption, assuming everything is at standard temperatures and pressures. So in this case, our del to G, our change in Gibbs free energy, is going to be equal to the change in enthalpy. So that'll be H2O, and that'll be the entry. So if this is gas, it's got to go to the second row, first column. And then we have to subtract away the enthalpy of, so we'll have H2, the first entry, but it's just 0, so that won't do anything, minus 0.5 times O2, the first entry. And then we have to do minus temperature times, it'll just ignore the spaces. Here we're going to have H2O, and we're going to have still the second row, but then the second entry to get the entropy. So we're coming in and getting this value, and then we're going to subtract away the second values for both of these two. So the first, we'll do the second value, and the second value. So this is the enthalpy term, and we don't even actually need the parentheses. And then if we want to compute, so if it's else, so if it's not greater than 373, if it's less than 373, then we'll do a different calculation, because we need to, now we're going to assume it's liquid water. So you have the first row, it's the liquid values, right? And then we're going to go in and we're going to calculate. So we have to end this. So we'll say E is equal to negative del G, and we're going to have to multiply this by 1,000, because this is going to be in, well, I guess we could, yeah, because this is going to be in kilojoules per mole. Same with this one, right? Then we have to divide this by N times F. So in this case, I usually like to put just kind of my fundamental constants, like Faraday's number 96485. This is Faraday's constant, and it's coulombs per mole. So it's basically the fundamental, it's the charge of the fundamental, a mole of the fundamental charge, basically. So so you imagine like you have a mole of electrons, how many coulombs is that? How much charge is associated with that? That's Faraday's constant. And then for this reaction, N equals 2. So this is the charge associated half reaction. All right, so if we went back and we looked at our notes for today, we saw, for this reaction, for the half reaction, so we wrote, you'll see there's 2 electrons in both half reactions, so it's 2, and they should be the same because they should cancel. All right, so let's run this and let's see what we get. So 1.22, and that's at room temperature. That seems about right. So let's see as we go up to maybe 400 or so. 1.15. So the issue with this is that not only does this temperature have an effect, and then going across a change in phase have an effect, but what might also have an effect is that your enthalpies and entropies are also a function of temperature. So you can't just assume that the same as what they are under standard conditions. So they're temperature dependent. So what we can do, right, is I gave you that table for the second problem. So this is calculating voltage at various temperatures. Right, and I gave you this table down here. Sometimes what I'll do is I'll take this table and I'll just put it in Excel. Right, and so what I can do is so here's it in Celsius. I just added 273 to put it in Kelvin. And then so I copied this. And then what I can do is I can come over here and I can just make some variable, A equals 1. And then that'll open up my A variable. And I can paste in these values. I try to paste them in here. So otherwise, if you try and paste them right in here, it's not going to work. So you have to come in here now. You can copy these. We can go into our editor. And so in this case, we can say del G matrix is equal to this. And what this basically is it has temperature and it has the delta G. And I've also plotted those here. Right. So temperature, the delta G as a function of temperature. Changing Gibbs free energy as a function of temperature. And so, well, the only issue here now is if we want to put in a certain temperature, or if we have the temperature from above, it might not be specifically one of these values that we can just look up. We need something in between. So there's a couple ways to do this. Probably the easiest way is usually to interpolate the data. So I know there's this help interp1 function, right? And if I look it up, I can see, okay, so if I have some function of x equal to v, right? And so I have some table of x and v's, then if I can query it for this, and what that basically does is it's going to, so let's say we had our delta G as a function of temperature, and it looks something like this. I'm just totally making this up. Probably doesn't look like this at all. But what it'll do is basically if you say, hey, what's the delta G at this temperature, it'll come down and it'll draw a straight line between these two, and it'll say, okay, where does it hit? And then it'll come over here. And so it basically breaks this thing down, breaks these data points down into a bunch of straight lines. And whenever you come down in between, it'll find it, and it'll come over, and it'll find the delta G's. So it'll do it this way. So so that's kind of how this interpolation will work. So what we have to basically say is so we'll say that del G, the actual delta G that we want, is equal to interp1, and we're going to give it del G matrix, and we're going to do the entire first row, all the rows, and the first column, right? And then we're going to do del G material, and we're going to do all the rows second column, and we're going to query it at this temperature in Kelvin. And query just means we're going to put that, we're going to look up, interpolate for this table. Right, so that's like, so interp one is just a kind of like this kind of table lookup, and you could and the default is just to do a linear interpolation. So another way you could do this is if you had this data, you could put a trend line on this data, right? And maybe not a linear across all the data, because that's going to be much worse than even the linear interpolation. But if you got this thing up to maybe, looks like, 5 orders, it's follows it pretty good. And so you can display the equation on chart, right? And some of the issue here is you'll notice that you only have like 1 sig fig in this data. So we're gonna have to, what we're gonna want to do is we're gonna have to go to text options, label options, and then we're gonna go to scientific, and we'll maybe, we should do at least 3 decimal places so that we have 4 sig figs just to be safe. So I'll take this, and so now I have this nice equation that fits my data. I can bring this over to MATLAB, right? So I'll call this, so we'll call this del G I for interp, del G F for the fit, and so we have this E, and we have to do, this is times T raised to the 5th. This is times T raised to the 4th times T raised to the 3rd times T squared. This is times T. Right. And so, and now we can calculate maybe our second guess using interpolation. So E2, and that's going to be the same as this. Right, and then we'll have an E3, which is going to be equal to, so this is del G of interpolation and del G of for our fit. And let's see how these compare. So let's do, so most of this data was for 298. So all this data should mostly agree, relatively close at 298. All right, so 1.22, so it's all the way down to the 4th digit. They all agree at this low temperature. Let's pop it up 100 degrees. So let's go to 398. Let's go to 374, just over 100 degrees Celsius. Right. So you see these two methods agree pretty well. They're just different by this, 0.05 here. And they still agree pretty well with our first method. All right, so let's bump it up a little bit more. Let's go to 500. So these two are still pretty close, and they should be because we're just fitting those functions. And this one's still doing pretty. This one's still holding pretty strong. It's first E. So let's really bump it up. Maybe we can start to see the differences. So now this is back here to this, to the differences are all the way back here with this, third digit. So we can see, these two are basically the same because you're basically doing the same thing, just a different way to interpret the data. And this one, and this one, we're kind of assuming that the changes in enthalpy and entropy aren't really changing, and really the only effect is this temperature in here. So with that, I think that's kind of the little short I wanted to do to get us doing a few calculations, doing a couple if statements, making vectors, modifying vectors, doing a little interpolation. I think at this point that should we'll be ready to go to do a little bit more advanced calculations in the next section. All right. Well, see everyone next time.